So far this semester, we have been talking about two kinds of physical systems. Right? And there are two physical systems which are really quite different from each other, but it turns out that the phase diagrams have something in common. Okay. So the first one was the Ising magnet. And here we have a phase diagram that looks like this, right? So in terms of magnetic field and temperature, we see a phase boundary that goes along the temperature axis and ends in a critical point. Right? So this is temperature, and then here we see a boundary, and that's the critical temperature. And then we looked at the gas-liquid transition. And here, the variables might be pressure and temperature. So yeah, let's label this as pressure, here as temperature. And there's some phase boundary that comes up and ends in a critical point there. I'll make that in black. It ends in a critical point there. And so here, there's a critical temperature and a critical pressure. And so we know that if you cross the solid line in either case, there's a discontinuity in an order parameter, right? So if you cross the solid line like that or like that, then there is a discontinuity in the order parameter, which is in the magnetic case, that's the M. The same kind of thing in the gas-liquid problem. Going this way, there is a discontinuity in the volume order parameter, the volume per molecule.
Excuse me, is there any biphasic coexistence in Ising magnet in that black line?
If you could specify the magnitude of the M, that would be like specifying the volume, right? And so in the gas-liquid transition, there's no biphasic coexistence if you work at constant pressure and constant temperature, but only if you work at constant volume and constant temperature. Right? So similarly with the Ising magnet, there is no coexistence if you work at constant field and constant temperature, but there would be if you work at constant magnetization and constant temperature. Now, it's harder to work with constant magnetization than with constant field. So that doesn't come up so often, right? Whereas with a liquid gas system, it's not so hard to work at constant volume. And so that's why we would talk about it more in the case of the liquid gas system, but there's still the analogy there. Yes, yes. Okay, good point. So these situations, right, where there's a discontinuity in the order parameter, which is either magnetization or volume per molecule, these things are both called first order phase transitions. So first order means a discontinuity in the order parameter. This and that. And as you get closer and closer to the critical point, the magnitude of the discontinuity gets smaller. And then when you reach the critical point, the magnitude of the discontinuity goes away. And beyond the critical point, there's no more discontinuity. There's a smooth evolution from one phase to another. So we could also say, what happens if we approach the phase transition by passing right through the critical point, right? So it could be a path reducing temperature like that, or like that. And in either of these cases, we could be reducing temperature, or we could be going on some diagonal path like that, right? In the liquid gas case. In these cases, passing through the critical point, there is no discontinuity in the order parameter. So in this path, we would say M is continuous, but the derivative of M with respect to temperature is discontinuous. Oops, discontinuous, right? Or likewise, in one of these green paths in the gas-liquid transition, the volume per molecule is continuous, but dV dt is discontinuous. Yikes, I missed a letter there. Discontinuous. Okay, these phenomena.
You wrote DV, Jonathan.
I'm sorry?
You wrote DV, DV.
Oops. Thank you. DVD, whoops, DVDT. Thank you. In these situations, right, these would be called second order phase transitions. So in both of these phase diagrams, there's a first order transition everywhere along the black line, except right at the critical point. Right at the critical point is the second order phase transition. All right, now, these are two different models. Well, they're two different experiments, and we developed two different models for them, which are quite different from each other. But they're showing this similarity in the results, right? And so now, a natural question would be, is there any fundamental reason why they should be similar? And would we expect to see similar kinds of behavior in other phase transitions? And if we look at a new phase transition in superconductivity, for example, or something else, would we expect to see related kinds of behavior? So there is a theoretical approach which gets at this concept in general. And that's what I would like to tell you about today, and probably in the next class also. So the approach that I want to show you is what's called Laudau theory. which is after the great Soviet theoretical physicist, Lev Landau. And it is a theory which intentionally ignores microscopic details of the world. Right? And so the idea here is that we don't think about the microscopic pieces like magnetic spins or atoms and molecules. We pretend that we don't know that the world is really made of atoms and molecules. And we imagine that the world is made of order parameters, right? That is, we think about order parameters. We think as if order parameters are the fundamental ingredients in the theory. And then we say, well, what can we figure out about the world just by thinking about order parameters and forgetting about spins and atoms and molecules? Right? And you might think we can't figure out anything about the world, right? If we don't know what the world is made of. But remarkably, we can. Right? And this was the great insight of Landau, is that we can figure out a lot about phase transitions if we just have fundamental assumptions about the smoothness of functions and about symmetry. And so this kind of theoretical approach is what I like to call, how to get something for nothing, right? That we're starting with almost nothing, right? We're starting with almost no knowledge of the world. And it's really remarkable that we can just figure out things about phase transitions based on these really basic, simple assumptions. Now, we cannot figure out everything, right? We can't get everything for nothing, but we can figure out some phenomena. And so that's remarkable of itself. So to show you how this works, let's go back to the Ising magnet. So if we want to do Landau theory for the Ising magnet. All right, so all that we know in the beginning is that there is some magnetic order parameter. So we'll call it M once again. And we would say the magnetic order parameter is equal to 0 in the disordered phase. And it's not equal to 0 in the ordered phase. Okay, and now let's suppose we want to figure out what's the free energy in terms of this magnetic order parameter. Well, at first you might say, Well, how do we know anything about the free energy, right? The free energy could be any old function of the magnetic order parameter. Okay? Now we bring in the first assumption, the assumption of smoothness. So we want the free energy as a function of m. Okay. So let's assume smoothness. That is, we assume that the free energy must be a smooth function of m, right? That as we change m, we don't have any sudden jumps in the free energy. We don't even have discontinuities of the derivative of the free energy. Right? We would say that the free energy and all of the derivatives of the free energy must all be nice, well-behaved functions of m. For those of you who have studied the calculus of complex variables, there's a technical word for this. That is an analytic function. So if you know what that means, great. That's what I'm talking about here. If you haven't studied analytic functions, let's just use the sort of casual word smooth to mean a function that's well behaved and all of its derivatives are well behaved. So we know that the output of our theory is going to be a phase transition. Right? So the output of our theory is going to be something that's not smooth. Right? A phase transition is not smooth. Right? When we cross a boundary like this in a phase diagram, something not smooth happens. Right? There's some discontinuity there. But we want to say that the not smooth behavior is the output of the theory. It's not the input into the theory. We want all the input into the theory to be smooth functions. And then we want to say, well, how could the output of the theory possibly be something that's not smooth? Right? So that is what will give sort of restrictive predictions. Okay, so to use this assumption about smoothness, let's go to the idea of a power series, a Taylor series. Okay? So whenever you have a smooth function, you can expand it in a Taylor series. Now, when I've shown you a Taylor series before, that was always in situations where we knew what function we want to work with, right? And then we figure out what's a Taylor series to represent the known function. Here, we don't have a known function, right? We want to know what is f of m. We don't actually know it in advance, okay? But we could say, whatever it is, if we assume it's a smooth function, there must be some Taylor series to describe it. Right? So let's just make up a Taylor series for f of m. Okay? So we could say f of m is, we'll expand it in a Taylor series about m equals 0. Okay, so f of m is some f0, whatever is the free energy when m is equal to 0, plus a first order term. So the first derivative of f with respect to m, evaluated at m equals 0, times m. plus a second order term. So 1/2 f double prime of 0 times m squared plus 1/3 factorial f triple prime of 0 times m cubed plus 1/4 factorial f quadruple prime of 0 times m to the 4th plus ... right? So higher order terms, which get smaller and smaller, assuming that m is some small magnetic order parameter. Okay, so this is an expansion, okay? And so it says, here we're basically taking all the information that we don't know and expressing it in the form of these coefficients, right? This, right? All of these coefficients are unknown parameters, but we can at least work with them. Okay, so now what can we do with this expression for the free energy? Okay, well, the next thing is we want to use symmetry. The idea of symmetry is that positive m and negative m are equivalent to each other. That is, for example, m equals positive 0.2 and m equals negative 0.2, right? These are the same physical state, except that one of them is pointing up and the other is pointing down, right? So this one is mostly, well, I was about to draw spins, but I won't draw spins because I'm pretending I don't know about spins, right? But this one is small magnetic order in the up direction. And this one is some small magnetic order in the down direction. So these are two different directions of magnetic order, but they're the same magnitude of magnetic order. And so because of the symmetry of this system, these are equivalent physical states. So they should have the same free energy. Likewise, m equals positive 0.3 and negative 0.3 should have the same free energy. Okay? So mathematically, that means that f of m must be an even function of m. That means that in the power series, we must have only even terms, right? If we had any odd terms in the power series, they would spoil the symmetry, right? And give unequal free energies for these two different states, right? So that gives us a constraint of only even terms in the power series, the Taylor series. So that would tell us f of m could be the 0th order term plus no first order term. So then there could be the 2nd order term. So a half f double prime m squared plus 1 over 4 factorial f quadruple prime times m to the 4th. Plus, in principle, there could be higher order terms. Okay, so this is symmetry coming into the theory. Now, let me do a change of notation just to make things a little bit simpler to work with, all right? So let me lasso this and copy this onto the next page. All right. Okay, so now, because we think the free energy should be an extensive variable, that is something proportional to the volume of the system, right? If we have a system that's twice as big, we ought to have twice the free energy, right? So let's just normalize everything by the volume. So I'll divide through everywhere by the volume. And this free energy per volume, I will call little f. And then this term, the 0th order term, I'll call this thing little f 0. And this I will call A. And this whole thing, this 1 over 4 factorial f quadruple prime, I'll call that just 1/4 B. Okay, and so this is just to have easier things to work with. And so that means here B is equal to 6 times f quadruple prime of 0. Since I didn't know what these coefficients were anyway, I can take something I don't know and multiply it by 6, and it's a different thing that I don't know.
I have a question.
Oh, question?
Yeah. About f being an even function.
Mm-hmm.
So you said that for same magnitude but different signs of magnetic order, you get the same value of f. When we worked on the interaction model, there were 2 mechanisms through which the free energy could change from the magnetic field and the interaction. And I remember the shape of the curve tilting a little bit with an angle sort of because of the interaction. And in that sense, with different values of m, you might have different values of the free energy. So how do you reconcile that with this assumption that
Excellent question. Let's let h equal 0 for now. Okay, so I will put in the fields coming up later. Okay, but for the moment there will be no magnetic field. Right now, so if there is a magnetic field, then of course there must be an odd term to represent the effect of the magnetic field. Excellent point, right? And so I'm leaving that out for the moment, but I will put it in shortly. Okay, but before that, let's say now, let's think about temperature. How does the free energy depend on temperature? Okay. Well, so we know from the examples that we've dealt with so far, right, that the free energy is a function of temperature as well as M, right? And so it's not just a free energy of M, but it's a free energy of temperature and M. Okay? So that could go into the theory here by saying that all of these coefficients could be functions of temperature. So it's F0 is a function of temperature, and A could be a function of temperature, and B can be a function of temperature. So all the information about the temperature dependence is embedded inside of these functions of temperature. Now, once again, we don't know how they depend on temperature, but let's assume that these things are smooth functions of temperature. That goes along with the whole spirit of what we're doing. Okay, so F0 of T and A of T and B of T are smooth, that is analytic, functions of temperature. Okay. So, if we want to make a plot of what they might look like, okay, so a typical plot would be something like this, that there's some A of T, which is some smooth function like that. And there's a B of T, which is some other smooth function. Now, I claim that the interesting behavior is what happens close to the point where A passes through 0. Okay, so you have these axes, and there might be some point when A passes through 0. Let's call that a temperature T0. And I will prove to you that the interesting behavior is near T0. So let's suppose that we're going to concentrate on temperature near T0. That is to say that T minus T0 is small. In that case, we could express A and B as power series about T0. So we could say A of T is equal to a constant, the value of A at T0. That's 0. Okay? So it's 0 plus a coefficient, call it A prime, times T minus T0, plus higher order terms. And B of T is its value at T0, so that's this thing, B0. B0 plus B prime T minus T0 plus higher order terms. And F0 is, again, a constant F0, 0, whatever you call it, plus F0 prime t minus T0, right, etc. Now, we are going to concentrate on the lowest order terms to give us the simplest possible predictions. So the lowest order terms are this thing, and over here, this thing. So we're going to put those lowest order terms into the expression for the free energy. So what do we get? Okay, we get a free energy.
Before moving on, can I ask a question?
Please.
Is there any special reason why you are keeping terms of Taylor series up until the fourth order term? I think you are doing this, right? You're keeping...
In the power series here, for example.
Right.
Yes, I am intentionally going up to the fourth order term because I know that that is what I will need to get a sort of minimal theory for the magnet, okay? And I'll show you in a few minutes what happens if I have fewer or more terms than that.
Okay, thank you.
Mm-hmm. Great. So, as Cheng said, going up to the fourth order term, right, I have a free energy on pen, which is F0, I'll just do it with 1, 0, F0 plus 1/2 A prime T minus T0 M squared plus 1/4 B0 M to the 4th plus dot, dot, dot. Okay, now let's think about what this function looks like at different temperatures. So first, let's consider if T is greater than T0. In that case, I could make a plot for F as a function of M. Okay? So when M equals 0, this function starts here at F0. Okay? And then when M is small, this quadratic term shows the leading behavior, the change in the free energy. So this will be going up like a parabola.
You haven't decided the sign of A prime yet, right?
That is true. I will tell you in typical physical systems, A prime is positive. Okay? And we can later get into the reasons why A prime is positive. But let's just assume for the moment that A prime is positive.
Okay.
Usually A prime is positive. So in that case, assuming A prime is positive, it looks like a parabola going up. And then we get to larger M, and then the quartic term becomes important. Okay. Now you're going to ask me also, we don't know the sign of B0. Is it positive or negative? Well, let's suppose it's positive. in that case, then the quartic term will make F go up even more. So we'll have a shape like that, okay? And then the minimum is at m equals 0. So this is the disordered phase. Okay, now suppose that the temperature is just equal to T0. So I'll draw that here. All right, if T equals T0, then we would get a plot for the free energy, which again starts at F0. And now the quadratic term is 0. So this plot is very flat near the minimum. But then the quartic term makes it go up. Okay, so this looks like it's coming around like that with a very flat minimum. So once again, the minimum is at m equals 0. So again, it is disordered. But now, suppose T is less than T0. In that case, we get a plot like this. Again, it starts at F0, but now the quadratic term is negative. So the function tends to look like this. It goes down, right? It's a parabola upside down, close to m equals 0. And then when we get to larger m, the quartic term becomes more important, and that's positive, so it makes F turn around like this. And we get a function with this kind of shape. And now we can say the minima are not at 0. The minima are there and there. We could call it positive and negative m0. So the minima are at m equals plus or minus m0. And now there is an ordered phase. So this is the same sequence of shapes that we saw, right, from the mean field theory, right, as I was varying temperature. But here I'm not putting in any assumptions about energy and entropy associated with these spins. I'm not putting in any assumptions about spins at all, right? It's just coming from these symmetry considerations. Okay, now let me show you one more thing and then I'll come back and answer Cheng's questions. Okay, so let's say we wanted to actually calculate the minimum algebraically. Okay. So if we have this equation for F, which I will copy and paste, copy, paste, okay. And so if we want to find the minimum, that means we'll take df dm equals 0. Okay? So that means if we just calculate the derivative, a prime T minus T0 M plus B0 M cubed equals 0. So M equals 0, or A prime T minus T0 plus B0 M squared equals 0. So we know that this solution is the minimum for T greater than T0. It's the maximum for T less than T0, okay? But the other state we would get by solving the quadratic equation over here, right? So that's B0 M squared is A prime T0 minus T. So M is plus or minus the square root of A prime T0 minus T over B0, which means that it's something which scales as T0 minus T to the beta power, where beta is equal to 1/2. Right? So not only am I seeing a phase transition where the shapes of the free energy plots look like what we had in in-field theory, but also I even get the same kind of prediction for how the magnetic order parameter depends on temperature, close to the phase transition. So, this is remarkably good agreement with what we did before, considering that I started with nothing, right? And so, that works pretty well. Now, it's not perfect agreement. So one way that you can see that the agreement is not perfect is that if you make the plot of M versus T, here in Landau theory, it's just a square root, right? So it keeps going up. So it keeps going up like that, right? Whereas we previously found that it goes up, but then it levels off, so that it has a maximum at plus or minus 1, okay? So this is something that I discussed with a couple of students when we were working on the first homework set, right? That the prediction of Landau theory looks like the prediction of our mean field theory around here, close to the transition, but not everywhere, right? This is how, you can't get everything for nothing, right? You only get the behavior close to the critical point, not the behavior far away from the critical point. Now, coming back to Cheng's questions, okay? So one of Cheng's questions had to do with the sign of this A prime variable, okay? We can see that the sign of A prime is positive, that positive sign goes along with the idea that we have the disordered phase at high temperature and the ordered phase at low temperature, right? If A prime were negative, it would be the other way around, right? If A prime were negative, then we would get order at high temperature and disorder at low temperature, okay? Physics doesn't usually work that way, right? Usually, high temperature favors a high entropy state, which means a disordered state. So in these normal physical situations, A prime is positive. Right? There could be a few weird exceptions, but this is the typical kind of physical behavior. Okay, now, why did I include the m to the fourth term, right? That was another question. You can see what would have happened if I didn't include the m to the fourth term. Right? If I didn't include it, then this function would go down and it would just keep on going down on both sides. Okay, so there would be no minimum, right? M would be driven to be positive or negative infinity. Right? In other words, the system would not be thermodynamically stable. And so I need the m to the fourth term in order to have something that is thermodynamically stable. That works as long as the coefficient of m to the fourth is positive. If that coefficient is negative, that would not work, right? So if the B0 were negative, then we would need to put in a sixth order term in order to have stability, right? So whatever is the highest power of m, that better have a positive coefficient. Otherwise, we would have a system that is not stable, that does not have any finite minimum, but the order is just driven to be positive or negative infinity. So in the simplest case of a magnetic phase transition, the fourth order term is positive, and that is what provides the stability. And then we don't need the sixth order or eighth order or higher powers. But there can be other situations where the fourth order term is negative, and then we need to include the sixth order term in the theory.
Okay, thank you.
Okay, so those are the answers for Cheng that I was postponing. I'm still postponing the answer for Dan about the magnetic field. And maybe I better do that one on Wednesday, okay? So I'm gonna stop talking for the moment and invite any other questions, and then we'll continue on with the magnetic field on Wednesday.